Langchain Azure Dynamic Sessions Tool Summary. A detailed overview of the langchain Azure Dynamic Sessions tool, highlighting its purpose, functionalities, requirements, and potential challenges. A powerful tool that leverages the Azure OpenAI service to provide dynamic conversational experiences. It facilitates engaging interactions by maintaining and utilizing session context, enhancing the natural flow of conversations. Inputs. User-provided text input, serving as the starting point for the conversational interaction. It captures the user's query or message, initiating the dialogue process, represents the accumulated knowledge and information gathered throughout the conversation, enabling the tool to maintain context and provide consistent and relevant responses. This context could include past interactions, user preferences, or any relevant external information. Outputs. The tool generates a comprehensive response based on the user input and session context, offering informative, engaging, and contextually relevant answers. It aims to provide valuable insights and address the user's needs effectively. Steps. The user-provided text input is received and analyzed to extract key information and understand the user's intent. The tool updates the session context by incorporating the latest user input, enriching the conversational history and enabling context-aware responses. The Azure OpenAI service is invoked to generate a response based on the user input and the accumulated session context. This leverages the power of large language models to produce coherent and insightful responses. The generated response is returned to the user, providing a comprehensive answer to their query and contributing to the ongoing conversation. Prerequisites. Azure OpenAI Service, a cloud-based service offered by Microsoft Azure that provides access to powerful language models, enabling natural language understanding and generation capabilities. It requires the following credentials to establish a connection and utilize its functionalities. Application Programming Interface Key, a unique identifier that grants access to the Azure OpenAI service, ensuring secure communication and authorization. Resource ID, a unique identifier that represents the specific Azure OpenAI resource, enabling the tool to locate and interact with the desired language model. Deployment name identifies the specific language model deployed within the Azure OpenAI service, allowing the tool to select and utilize the appropriate model for the conversational interaction. Azure Storage Account, a cloud-based storage service provided by Microsoft Azure, offering scalable and durable storage for data. This is required to manage the session context efficiently, storing and retrieving conversational history to ensure consistent and context-aware responses. It requires the following credentials. Account name, a unique identifier that identifies the specific Azure storage account used for storing session context data. Connection string, a set of configuration parameters that enables the tool to connect to and access the designated Azure storage account, facilitating data transfer and management. Fine-tune parameters. Temperature controls the creativity and randomness of the response generated by the Azure OpenAI service. Higher values promote more creative and diverse responses, while lower values lead to more deterministic and focused outputs. Top K limits the number of potential words considered during the response generation process. A lower value restricts the model's vocabulary, producing more focused and coherent responses. Top P similar to Top K, but instead of restricting the number of words, it restricts the probability of the model selecting specific words. This helps in controlling the likelihood of generating unexpected or irrelevant words. Challenges and fixes. Session context management issues. Maintaining an effective session context is crucial for providing coherent and relevant responses. The challenges associated with this include managing the size of the session context as the conversation progresses. The session context can grow significantly, potentially affecting the performance and responsiveness of the tool. Utilizing a vector database, a specialized database designed for storing and querying high-dimensional data, such as textual data, can be employed to efficiently manage and retrieve relevant information from the session context. Azure OpenAI Service errors. The Azure OpenAI Service, like any other software service, is susceptible to errors. These errors can arise due to various factors and can significantly affect the tool's functionality. Some common causes and solutions include verifying API key. Ensuring the accuracy and validity of the API key is essential for successful communication with the Azure OpenAI Service. Checking deployment status. The language model deployment needs to be active and accessible for the tool to generate responses. Implementing error handling. Robust error handling mechanisms should be implemented to gracefully handle unexpected errors, providing informative messages to the user and maintaining the tool's stability. Challenges and fixes. Challenge 1. Selecting optimal lambda parameter. Fixes to challenge 1. Experimenting with different lambda values, ranging from 0 to 1, allows users to observe the impact of this parameter on the retrieved documents and ultimately identify the optimal value for their specific task. Challenge 2. Handling large document sets. Fixes to challenge 2. Using efficient document indexing and retrieval methods, such as vector databases or search engines, can significantly improve the performance of MMR retrieval, especially when dealing with massive collections of documents. These methods enable faster document lookups and retrieval, making MMR retrieval scalable for large datasets. Langchain Astrad B utils MMR cosine similarity summary. This describes the process of calculating cosine similarity between two vectors using the langchain library with Astra DB as the data storage. The cosine similarity score is used to assess the similarity between two vectors, with a score of 1 indicating perfect similarity and a score of 0 indicating no similarity. Inputs. This refers to the numerical representation of a query. This is a vector representing the meaning of the query, generated through techniques such as transformers, which are language models that learn to represent words and sentences as vectors. For instance, in a search engine, the query "What is the capital of France?" will be translated into a query embedding vector. This represents the numerical representation of a document. Similar to query embedding, this is a vector generated using techniques like transformers, representing the meaning of a document. Each document in the data store, like a document in a document search engine, will have a corresponding document embedding vector. Outputs. The output is a numerical score between 0 and 1. Representing the cosine similarity between the query embedding and the document embedding. This score indicates the degree of similarity between the query and the document based on their respective meaning representations. For example, if the cosine similarity score is close to 1, it suggests that the query and document are semantically similar. Conversely, a score close to 0 indicates a low semantic similarity. Steps. This involves calculating the dot product of the query embedding and the document embedding. The dot product is a mathematical operation that measures the alignment of two vectors. A higher dot product indicates greater alignment between the two vectors. In the context of semantic similarity, this step measures the alignment of the meaning of the query and the document based on their respective vector representations. This refers to calculating the magnitude of the query embedding. The magnitude of a vector is a measure of its length. In this case, the magnitude of the query embedding reflects the strength of its vector representation, indicating the degree of information encoded in the vector. This involves calculating the magnitude of the document embedding. Similar to the query embedding, the magnitude of the document embedding represents the strength of its vector representation. This step involves dividing the dot product of the query and document embedding by the product of their magnitudes. This operation effectively normalizes the dot product, ensuring that the resulting cosine similarity score remains within the range of 0 to 1. Regardless of the magnitudes of the query and document embedding vectors. Prerequisites. An Astra DB instance is a cloud-based database service offered by DataStax that is used for storing data. This step ensures that the data required for embedding calculations, such as the documents and their associated embeddings, is available and accessible. Langchain is a library in Python that simplifies interactions with large language models, like those used to generate embeddings. The langchain library is a prerequisite for this process as it provides the necessary functionalities to work with embeddings, such as calculating the cosine similarity, fine-tune parameters. This step is not applicable to the described process, implying that the cosine similarity calculation does not involve any use of adjustable parameters. This indicates that the process is a fixed calculation based on the input vectors and does not require fine-tuning based on specific preferences. Challenges and fixes. This refers to a potential issue where the dimensions of the query embedding and the document embedding do not match. For example, if the query embedding has 100 dimensions and the document embedding has 200 dimensions, it will not be possible to calculate their cosine similarity. The solution to this challenge involves ensuring that the query embedding and the document embedding have the same number of dimensions. This can be achieved by either padding the smaller vector with zeros or by truncating the larger vector to match the smaller dimension. This refers to a potential scenario where the cosine similarity calculation results in a non-score, not a number. This can occur if either the query embedding or the document embedding has a magnitude of 0, leading to a division by 0 error. The solution to this problem involves checking for 0 magnitude vectors. If either the query embedding or the document embedding has a magnitude of 0, then the cosine similarity score should be set to 0, indicating no similarity between the query and document.